Today our topic of concern is ionic equilibrium. So ionic equilibrium is the second phase which we will learn in the equilibrium chapter. The first phase was chemical equilibrium and the next one is the ionic equilibrium. So what is the difference between this chemical equilibrium and ionic equilibrium? Let me elaborate. In chemical equilibrium, we have seen that most of the molecules, either they are in the gaseous form or they are in their solution form. These are mainly taken according to they're calculated according to their active masses. Okay, here the thing is same, but a little bit of difference is there, because here what we will consider mainly is about acid, bases and salts. Salts mainly the hydrolysis of the salts, as well as the what is it said, the hydrolysis and the solubility product. Okay, so these are the few differences between the ionic equilibrium and the chemical equilibrium. Now when we start ionic equilibrium, we have to start with a law. Okay, this law is known as Ostwald dilution law. Okay, this law is known as Ostwald dilution law. Now, in Ostwald dilution law, we will see that this law is mainly concerned about weak acids and weak bases. Okay, because strong acids and strong bases completely dissociates in solution phase, and weak acids and weak bases, they do not dissociate completely, they dissociate partially. For complete dissociation, we know we can calculate the pH as negative logarithm of hydrogen and concentration. pH is negative log to the base 10 of hydrogen and concentration. But what about the weak acids, where the dissociation is very less compared to its original volume? Okay, so here we will learn about their degree of dissociation. It is same as that we have learned about in Kp, that this is the amount Kp and Kc. This is the amount that will be dissociated in a chemical equilibrium. Same thing here we will see. There we are concerned about reactions. Here we will be concerned about dissociations. Okay. In chemical equilibrium, the main concern was reactions. Reaction between two entities to give out a third entity. That can be in the gaseous form, that can be in the solution form, that can be in the solid form. Here we will mainly be focused on dissociation. Okay. Now, what is Ostwald dilution law? Ostwald dilution law is the degree of dissociation of a weak electrolyte. The degree of dissociation, of a weak electrolyte. The degree of dissociation of a weak electrolyte, okay, is directly proportional to the to the square root of its volume, and inversely proportional to the square root of its concentration. Okay. Now, this is the statement, or this is the definition that the law states, what the law states for Ostwald dilution by Ostwald. Now, in chemistry, everything is backed, every law is backed by some evidences, the reaction evidences. Suppose I have a weak acid. Let us say I am having acetic acid, which is an organic acid and a weak acid. It dissociates in solution as CH3CO minus and H plus. Okay. if I use water here, then it will be H3O plus. Okay, if I am going to use water here, okay, plus water here, then this H plus would have been formed as H3O plus. Okay, but let us not go to that part. Let us understand what it is. So initially, this was, you can say the concentration was C, initial concentration. Initially, this was C, this was 0, and this was 0. Same like that of our chemical equilibrium. After degree of dissociation alpha, after degree of dissociation alpha, okay, after degree of dissociation alpha, so it will be C minus C alpha, and it will be C alpha, and this will also be C alpha. C minus C alpha, C alpha, and C alpha. Now, according to the equilibrium, okay, what did we know? That it will be concentration of the CH3CO minus concentration of H plus over the concentration of CH3COOH. This is C alpha. This is also C alpha divided by C. You take common and you will write in brackets 1 minus alpha. So one of the C will get cancelled and you will get C alpha square over 1 minus alpha. And as alpha is less than 1, so 1 minus alpha can be considered to be 1 as well. Okay, we can consider 1 minus alpha as 1. So we can write that K equilibrium is equals to C alpha square. Okay, we can write this. So this is the equilibrium constant of a dissociation of a weak acid. This is the equilibrium constant for the dissociation of weak acid. Now the weak acid we have dissociated is acetic acid. And as it is an acid, this equilibrium constant will have a new name. It is an equilibrium constant, but it will have a new name. It will be dissociation constant of the acid. It will be named as dissociation constant of the acid. Now, KEQ, this will be named as dissociation constant. Equilibrium constant will now become dissociation constant of acid. And KEQ will transform itself as Ka. Okay, it will be named as, it will be written as Ka. Understood? This is equilibrium constant. So we will write Ka is equals to C alpha square. Now alpha is equals to root over of Ka over C, root over of Ka over C, and we all know, so here this statement is becoming correct. It is inversely proportional. Who is the degree of dissociation of weak electrolyte, which is alpha, is directly proportional to the square root. We will come to this right now in a bit, and is inversely proportional to the square root of its concentration. This we have found it out. Now, what is concentration? Moles per volume, moles per unit liter, or moles per volume. So if you write here like this, root over of Ka moles per unit volume, okay, so you will get root over of Ka by moles times volume. Okay, so this degree of dissociation of weak acid is directly proportional to the square root of the volume as well. This is how we will understand. Okay, the two statements too are correct. If this is for a weak acid, then for the weak base, we will have the same thing. Okay, suppose we are taking a weak base. Now take an example of weak base. So an example of weak base is ammonium hydroxide. Okay, an example of weak base is ammonium hydroxide. It dissociates as NH4 plus and OH minus. Okay, NH4 plus OH minus. So this ammonium hydroxide, which dissociates like this, will be in equilibrium with each other. Okay, and you will do the same thing initially Okay, initially it will be C, this will be 0, 0. After degree of dissociation alpha, C minus C alpha, then C alpha and C alpha will be formed. And from here, in place of Ka or Keq, it will be written as Kb. That means it will be dissociation constant of base. Okay, so it will also be C alpha square over 1 minus alpha or C alpha square, because alpha is less than 1. Okay, this is how we will understand. And it is same, that is degree of dissociation of weak base, that means weak electrolyte, weak acid or weak base, these are all electrolytes. Weak salts, these are also electrolytes. But salts are generally not weak, they are either soluble or non-soluble. So either they will be hydrolyzed, they can be hydrolyzed, or they cannot be hydrolyzed. Like PbSO4, lead sulfate. Lead sulfate is a compound that is very hard to dissociate, hydrolyze in water, with water. Barium sulfate, okay, they are resistant to strong acids like HCl, HNO3. They are resistant to H2SO4 also. They will not dissociate in acidic medium as well. So they are the resilient salts. They do not undergo solubility, they do not undergo dissociation or hydrolysis easily. So this is the main thing. Now, these are all constants, equilibrium constants, and all equilibrium constants have same type of rule. That is, they are dependent only on temperature. So this dissociation constant of acids and dissociation constant of base, means weak acid and weak base, are only dependent on temperature. Okay, like equilibrium constant was dependent on temperature, here also we will learn that these constants Ka and Kb, dissociation constant of acid and dissociation constant of base, are also directly proportional to temperature. Only dependent, sorry, not directly proportional, they're only dependent on temperature. Okay, so higher the values of Ka and Kb, higher is the strength of the acid or base. Okay, higher the values of Ka or Kb, greater is the strength of the respective acids or base. Okay, respective acid or base. Okay, so it is dependent on this type. Now, if our acid is a monobasic acid, then this law holds very good. Okay, if this acids, as the acids are monobasic acids, this law holds very good. But what will happen if it is a diabasic acid? Okay, or it is a diacidic base. Suppose in place of acetic acid, I am taking oxalic acid. What will happen to that case? In that case, at a time, only one H plus will be dissociated. The other H plus will not be dissociated at a particular instant. So for that instant, we can calculate for a weak acid, weak dibasic acid, but directly using this form for a monobasic acid or a monoacidic base is a little tough, or you can say that it is a limitation of this Ostwald dilution law to predict the dissociation of weak dibasic diacidic or dibasic electrolytes. Okay, so this is one of the things. Next, we have to learn about why we are concerned about this dissociation of acids, weak acids and weak bases. What is our goal? What is our motive? Why do we want to see this dissociation? Because our agenda is to find out the pH of the solution, either the pH or the pOH. Mainly, we are concerned about the pH of the solution. We need to find out the pH of the solution. Now, how can we find the pH or pOH of the solution? How can we find out? We have already discussed that pH is the negative, P means potential, and it is the negative logarithmic of hydrogen ion concentration, and pOH is negative logarithmic of OH minus concentration. Even pOH can be written as 14 minus pH. Okay, that is pH and pOH. If we add them, you will get 14. Okay, this 14 is, it looks like some type of Ki, but it will be 14. Okay, it is 14. This pH plus pOH is also can be written as pKw. That means Kw is the dissociation constant of water. Kw is the dissociation constant of water. Okay, Kw. Kw equals to 10 to the power negative 14. So pKw is equals to negative log of 10 to the power minus 14, or first let me write it Kw, then I will write it negative logarithmic of 10 to the power minus 14, and pKw equals to 14. Understood? This is how we can say. So this is pH and pOH for strong acids and strong bases, and pKw is for the neutralization reaction, okay, between a strong acid and a strong base. Even for weak acid and weak base also, this neutralization reaction is occurring, but in neutralization reaction for weak acid and weak base, it is dependent on the how weak the acid is or how weak the base is. If the base is more weaker than the acid, then the solution will be acidic. If the base is stronger than the weak acid, means the weak base is stronger than the weak acid, then the solution will be basic. As simple as that. It is all dependent on the dissociation. Okay, higher dissociation of acid means higher amount of H plus present, and higher dissociation of base means higher amount of OH minus ions present. So suppose I have an acid A and a base B. In acid A, you are having 10 H plus ions. In acid B, you are having 15 OH minus ions. So overall, only 10 will get neutralized. The rest 15 will make the complete solution basic in nature.